Assalamu alaikum. So today we're going to consider the role of temperature, and we're going to see how lasers work. Next week we're going to discuss the second law of thermodynamics. So let's consider an example of a solid object. The walls are made up of solid, and there's a cavity inside this object. So it's a hollow object. So the atoms that make up the walls of the solid, let's consider the quantized vibrational levels of these atoms. So the atoms can be considered to be tiny masses which are attached to springs and attached with neighboring atoms. So there is vibrational kinetic energy, and of course this energy has to be quantized. We can draw a potential energy curve, and we know that the energy levels are quantized, and the spacing between these levels is constant. There is a ground state energy E0 and a spacing between the levels which is h bar omega naught, and so on. So this is a quantized version of the harmonic oscillator, and this potential energy diagram and quantized energy levels represent the vibrational energy of the atoms that constitute the solid. Now what we do is that we place this solid on a heating stove. So there's fire underneath, and it's heating the solid. So what we would expect is that the thermal energy and the internal energy of the solid would go up, and as a result the temperature has to rise. Now suppose this stove was off, everything was at room temperature. Now these are the vibrational levels of one particular atom. The question is that if we are at temperature T, which of these levels is populated? This is the question that we're going to answer. So suppose these are the quantized vibrational levels, and by population we mean that which level is the atom really at. In other words, what's the energy of the atom? So there are different possibilities. There's the ground state energy, there's the n equals 1 state, n equals 2 state, n equals 3 state, and n is going from 0 all the way up to infinity. So there is an infinite number of levels that the atom can reside in, or the vibrational energy could take up the value E0, it could take up the value E1, E2, and so on. But if this object is at the temperature T, which of these states is really populated? So this is a question I pose to you. Could you tell me what is the most, which state would you expect to be populated? E0. Why is that?
It's the ground state. More stable.
It's the ground state. It's stabler. It has the least energy. All right. So if I increase the temperature, I turn on the fire, the temperature goes up, which means the thermal energy is going up. This means that the random component of the vibrational energy has to go up. So as the temperature goes up, would your answer still remain the same? That then what happens? It could be one of the higher states, but those are excited states. So why don't you apply the same reasoning again, that E0 is the lowest energy state?
Come back to the ground state.
The heat is going to excite. Never say heat is exciting something. It's the transfer of energy to the atom that is increasing the internal energy.
Saying that the electron will de-excite.
The electron will de-excite.
Immediately and come back to the ground state.
So what is, when you increase the temperature, what's the most probable state that is populated? Is it still E0? No. So these are the kinds of questions we would like to really ask today. And the answer was provided in the 19th century by a scientist with the name Ludwig Boltzmann. अभी जो बोल्ट्जमैन था, he was a German scientist in the 19th century, और he was a great teacher. When he was giving his lectures, his auditoriums had always had to be moved on to the larger sites. But he was a very sensitive human being, and his colleagues used to criticize him quite a lot. So he ended up committing suicide. And on his grave is written not his name but a famous formula: S equals K natural log of W. So this is what is inscribed on his tombstone, and this is what we're going to learn next week about. But Boltzmann provided the answer to the question that I've asked you, and that was in the 19th century. Suppose you have all of these levels: E0, E1, E2, E3, and the object as a whole is at a temperature capital T, and this is an absolute temperature. So what Boltzmann proposed was that the probability that the level EI is populated is given by probability of occupancy of EI, and this is proportional to exponent minus EI over kBT, where T is the absolute temperature and kB is a constant that is honored after Boltzmann. It's called the Boltzmann constant. It has a value 1.38 into 10 to the power minus 23 joules per Kelvin. So the probability that a particular level is occupied is proportional to this factor, exponent minus EI over kBT. So what we could say at best is that if we have this harmonic oscillator at a particular temperature, we cannot be confident which level is populated. We cannot say with 100% certainty in most cases. What we can say is, at best, we can assign probabilities. There's a probability that E0 is populated, there's a probability that E1 is populated, a probability of occupancy of E2, and so on. So we can only assign probabilities. Now what I would like you to do is, suppose I draw a graph between the E's and the probability of occupancy. So I have E0 I have E1, I have E2, E3, and the solid is at a particular temperature. So could you please draw what this curve will look like based on the Boltzmann factor? The temperature is constant, yes. काम नहीं कर रही है ये ऑन करो इस तरह तो होता नहीं बोला जा रहा इसमें बैटरी बदलो रफली ठीक है लेकिन जरा दोबारा देखो रफली ठीक है रफली ठीक है लेकिन डिस्क्रीट लेवल्स पॉपुलेटेड है ठीक है दैट्स रफली ऑल राइट but the levels that are populated they are discrete नहीं हाँ but only discrete levels are populated ठीक है sorry roughly all right here that's fine which one hello all right so this is an exponential curve it has its maximum value when the energy is minimum so when the energy is minimum this is not by the way zero it's the ground state energy E naught so when this is E naught the probability is maximum and when we reach the next level which is E1 goes up it's higher than E naught the difference is h bar omega naught but since this is negative sign here this exponential becomes more negative and the exponent decreases so we get some probability associated with E1 some probability associated with E2 some probability associated with E3 some probability associated with E4 and so on and if we join the tops of these points because these are discrete levels I can't draw a continuous curve I'm not allowed to draw a continuous curve because the energy values are quantized however if just for my visual aid I draw a curve it will have an exponential decay it's going to decay exponentially another way to plot this is to do a semi-log plot that is plot the log of the probabilities so we have an exponential decay now what would happen this is at a particular temperature an exponentially decaying curve. Higher energies have less likelihood of being populated. Lower energies have a higher likelihood of being populated. And the likelihood is given by this factor. Second question. If I increase the temperature, that is, I turn on the fire, the thermal energy of these molecules, of these atoms, is going to increase. And what we expect from the Boltzmann factor is that there would be higher likelihood compared to the previous case for the lower temperature for the higher states to be populated. Because now this temperature is higher. Now, superimpose on the same curve, could you show me what the new curve will look like for the higher temperature? It's not really a straight line, it's exponentially decaying. Now I've increased the temperature. I would like you to draw a plot on top of this. It increase in temperature. बिल्कुल नीचे होगा. शाबाश, very good. Remember that the probability of occupancy of the higher levels, some of the higher levels, has to go up. Exponentially hoga. The curve is still exponential. The shape of the curve doesn't change. Shabash, good. Shabash.
Go up from here and be down from there.
So these are the kinds of questions I would like to ask in quizzes and exams. So you really need to have an understanding of the Boltzmann factor. If I increase the temperature, this factor does not change in its functional form, it's still exponential. However, the probability of occupancy for the higher energies is going up. So this curve starts from a lower value because now T is higher. If T is higher, this factor is smaller, and since it's a negative, this factor as a whole is larger. So the curve would go something like this. It's still exponential, it's not going to rise, of course. So the probability of occupancy of the first level goes slightly down. The probability of occupancy of the second level is still smaller than the previous case, but then it starts to rise. You can't be sure? So for some of the level, I mean, this is just, I don't have numerical values of T and E right now, but if I do have the numerical values, I can draw a curve with certainty. But this is the general shape the new curve will take. It's going to decrease for the first level, of course it is, and it's going to rise in general. We don't know which level has a higher probability now because we don't know the precise values of T and EI. So the point is that it has to go down for the smallest energy level. And why is that? Because the area under this curve has to remain the same, has to remain equal to 1. So if it's going up for the higher energies, it has to go down for the smaller energies. What if I make the temperature go to infinity? Let me ask this question in a different way. Suppose I have, now this is very important discussion, so please pay attention. Inside the walls of the solid, I have a large number of atoms and a large number of harmonic oscillators. Suppose I have n atoms, n oscillators. And in each one of them, the energy levels are quantized. So these are identical oscillators. And the solid is at a temperature capital T. Now if I consider only one oscillator, there is a probability of occupancy of a certain level, correct? Given by the Boltzmann factor. If I have a large number of atoms and I'm looking at all of them, I'm looking at all of them together, which means I'm looking at the assembly of all of the oscillators. I'm not looking at one oscillator as I've looked at here. I'm looking at all of the oscillators that make up the atom, which means the solid, which means I'm looking at the assembly of oscillators. And this assembly has a very nice word in physics. It's called an ensemble. I'm looking at an ensemble of atoms. Now on average, if there are n oscillators, on average there will be a certain proportion of, a certain fraction of oscillators in which E0 will be populated, a certain fraction in which E1 will be populated, a certain fraction in which E2 will be populated, and so on. And those fractional populations will also be proportional to the Boltzmann factor. Is that clear? Because if I look at one atom and there's a probability associated with the occupancy of a level, then if I have an ensemble of atoms, then there will be a fraction of atoms in which EI will be populated, and that fraction will be given by the Boltzmann factor. Alright? So if there is a probability that E0 is populated and there's a probability is 80%, then if I look at all of these oscillators, 80% of the oscillators in 0.8 times n of the oscillators on average, I will find that the lower level is populated. So this is exactly 80% of the oscillators on average. And if there is a 20% probability that E1 is populated, then 0.2 over n, or 20% of these atoms in the ensemble will have E2 populated. So I can move from the picture of one oscillator to the picture of an ensemble of oscillators. Alright? And the Boltzmann factor discussion carries over to ensembles as well. So now the atom as the solid comprises zillions and zillions and zillions of atoms. And it's not possible for me or for anyone, even for a supercomputer, to draw all of those atoms. So there is a compact representation of diagrams of this kind. And that representation is the following. You just draw one oscillator. Then you draw the energy levels. E0, E1, E2, E3 and so on. And then you draw, say, if 80% probability is for E0, you draw 4 circles here. You draw one circle here. So this would actually represent that 80%, in 80% of the atoms, E0 is populated, in 20% E1 is populated. So I can draw up diagrams of arbitrary complexity. Now what happens if I increase the temperature? Alright. Suppose my oscillator is now at 0 kelvins. At 0 kelvins, which is roughly minus 273.15 degrees C. I'm at 0 kelvins. Now what I would like to do is, I would like to find the Boltzmann factor. Which of these levels is likely to be populated from an intuitive perspective? E0. At 0 Kelvin, I have vacuum. I have just the ground state energy. I have no thermal energy inside the atom. I have no internal energy inside the atom. So only the ground state has to be populated. Right? Which means that all of the atoms would lie in the state E0. And the total energy of the solid would be equal to the number of atoms n times the ground state energy. And this is a compact way of representing the entire picture. I've just drawn one oscillator and I put a large number of circles in it. Let me just finish, I'll answer your question. Now if I increase the temperature, some of the higher energy levels will be populated. Alright? For example, I can get some population in E1. I can get some population in E2. And so on. However, the thermal energy has to go up if I would like the highest levels to be populated. And remember that this gap is h bar omega naught. So if I am at 0 Kelvin and the probability of occupancy of E1 is 0 by the Boltzmann factor, if I would like to get some population in E1, I have to provide it with thermal energy, or I have to increase the internal energy by at least this much, by at least h bar omega naught. Otherwise, I will not be able to populate any of E1. Right? So this is the state at low temperatures. At higher temperatures, you would get successively higher populations in the higher levels. Now my question is, what if I make the temperature infinite? Just think about it for half a minute and then I'll answer your questions.
Only
the highest possible energy level.
The electrons will escape.
The bond.
Now, some students are asking that the bond will break. Suppose the harmonic oscillator is just there and there are infinite number of levels that can be occupied and the bond is not going to break. Suppose the ionization potential is also infinite. Now I place this on a stove and I place it forever. There's no heat, there's no loss of energy, there's no dissipation, there's no Q, and the temperature actually reaches infinity. The question I've posed is, what's the fractional population of the levels? Yes, right at the back. They will all be equal.
A straight line at the end of the
At the end, and what about at the beginning? Nothing? Anyone else?
I think they'll all only be at E infinity.
All of them will be at the highest level, infinity. E infinity, okay?
I think that this curve will be replaced like this.
It will go the other way around. It will go like this. Like this.
The probability will be 1, so the curve would be a straight line downwards because the area under the graph has to be same.
It has to be downwards.
Straight line.
It would just be a straight line hugging the
Straight line.
Exactly. The lady at the back and these two students have provided the correct answer. It's going to be an equal probability distribution. All of the levels will have equal likelihood of being populated. If this temperature T goes to infinity, exponent minus 1 over infinity is 0, which is 1. So there's equal probability. Each probability is proportional to 1, which means that each probability is equal. So what's going to happen is that there will be an equal likelihood of populating all of the states. No matter how small or large, we can find out what this probability is, what the height of these is. But there will be an equal probability of populating all of the states. And it's wrong to think that only the most excited level will be populated. So at infinite temperatures or very large temperatures, what we really have is an equal probability distribution. And so on. Alright, so these are very important concepts, so I'm going really slow for you to understand. Now, let's consider this very high temperature case. It's a very high temperature case. 1 minute, please. And suppose it's not infinity. So there is a slight preference to be in the lower states. Right? So this is our probability distribution. We are at a very high temperature, not really infinity, but this is the kind of tapering off of the probabilities that we've talked about because of the Boltzmann factor. Alright? Now what's going to happen is that these are excited states and this is the ground state. So an electron would like to jump from an excited state to lower energy states. So all kinds of transitions are possible downwards. And when these transitions are made, photons have to be emitted. So a large number of photons are being emitted into the system, into the surroundings. And could you tell me what would be the energies of these photons? H bar omega naught? Multiples of H bar omega naught. So there would be n times H bar omega naught. So eventually, if you let this process to go on forever, that is emission of photons, what you would expect is that only the ground level is populated. Everything is going to fall back down like a waterfall. It will fall back into the ground level because the higher energy electrons are being demoted. They come back and fall back to the ground state. But this then defies the Boltzmann principle, because the ground state, a complete population of the ground state is only possible for 0 kelvins. So what's going to happen is that when photons are emitted, if there are neighboring atoms, these photons can be absorbed by neighboring atoms, and those absorbed photons can result in excitations. So when you let the system to equilibrate, on average there are absorptions and emissions taking place together, and the rate of absorption and emission is such that this population distribution is maintained. Alright, do you understand this point? So if we look at this solid, the atoms of the solid are emitting photons, and those photons are going into the cavity. So there are photons inside the cavity. There is radiation inside the cavity. This is called cavity radiation. Now these photons are also being absorbed by the atoms because they are of the correct frequency. So if you let this process to equilibrate, eventually, which happens very fast, the population distribution will exactly match this, which is predicted by the Boltzmann distribution. Alright? So this radiation is called cavity radiation. It's also called black body radiation. So what's happening is, let me repeat this argument and listen very carefully because it's a subtle argument. Now there's a population distribution dictated by the Boltzmann law, by the Boltzmann principle. And that's a tapering off of populations as you go to higher levels, and the tapering off is exponential. Now since some of the excited levels are populated, electrons would like to come down to the ground state. Like a waterfall, everything should eventually come to the ground state, which means only the ground state would like to be populated. But that is not allowed, because if photons are being emitted, these photons are being absorbed as well by neighboring atoms. And when they absorb photons, excitations to higher levels are possible. So in a state of equilibrium, the rate of emission and the rate of absorption is adjusted in a way that the population distribution matches the Boltzmann relationship. Another aspect is that this cavity will have radiation or photons of frequencies n h bar omega naught, and this radiation will tell you what the temperature of the solid is. This radiation is called cavity radiation or black body radiation. Now there were a few questions I would like to answer one by one.
I was saying in that 0 Kelvin value, you don't consider the capacity of the shells, right, to hold a certain amount of electrons.
So it's a very good question. At 0 kelvins, this one shell or this one energy level has a large number of electrons. First, I'm not talking about electrons, I'm talking about atoms here. Even if I were talking about electrons, this diagram does not represent one atom, or all of these electrons may not be in one atom, because this is just a compact representation of all of the oscillators, right? So the Pauli exclusion principle always has to be satisfied. There were more questions. Aap puche.
All of the objects' energy would be due to its mass.
All of the energy would be the ground state energy. It's not necessarily equal to the mass. It's the energy inside vacuum.
Okay, then where does that energy come from?
So vacuum itself has a quantum structure. It has some energy in it. though that kind of energy is present inherently in the fluctuations inside vacuum. If you have a resistor, you place it in at 0 Kelvin, the motion of the electrons will not cease. They will still undergo random motion, Brownian motion. So it is this vacuum energy that actually explains how the universe was made. There was vacuum, the Big Bang occurred, the energy was created, but that energy had to come out from somewhere. That came out from vacuum. So zero state energy or ground state energy is there in vacuum. Even if there is nothing, there is energy.
How can nothing have energy?
Nothing is a word that we give out of our choice to anything. No more questions, Ji.
I missed this point. If it's about radiations, then why are not all the arrows pointing outside this cavity? Some are going in.
I mean, because these atoms are inside the walls, they are emitting photons, they are going into the cavity, and there is radiation going into the walls. It's a two-way process.
You said fractional populations are proportional to the Boltzmann constant. Isn't it a constant?
The fractional populations are not proportional to the Boltzmann constant. They are proportional to this Boltzmann factor. Right? This is not a constant. Only Kb is a constant. The probability of occupancy of the level EI is equal to some constant, let's call it A, exponent minus EI kBT. Could you help find what the value of A would be? Because I talked about proportionality, so there has to be a constant of proportionality. Could you tell me what this constant of proportionality has to be? Could you find this constant of proportionality for me?
And we can introduce the energy level finite.
Finite, infinite doesn't matter.
In the high temperature case you just did, were you saying that this cavity inside has a high temperature, so the equilibrium is the, like, I didn't get the question behind the explanation. I got the explanation.
The question was that if you have higher levels being populated, they would like to de-excite, and eventually everything would like to fall back down to the ground state. But the Boltzmann relationship does not allow that. The Boltzmann relationship says that there has to be a population distribution. Some of the high levels have to be populated. That was the question.
1 over sum of energy. 1
Sorry, no, not 1.
Sir, when like all the electrons, atoms go back to the ground state, for example, if we're talking about the electrons, so it does not mean that all of them will go back to the first state. They will like be arranged according to energy levels.
Right. That is dictated by the Pauli exclusion principle. They can't all of them go back to the same state. But here we're talking about a large number of atoms. They go back to the ground state, whatever the ground state is. It's not necessarily the lowest energy state in the atom. Is anyone exactly sure of the answer, and is anyone confident enough to quote an answer? पहले मेरा जवाब दो, फिर मैं दूंगा. मैं दूंगा जरूर, लेकिन you don't have to take a course on probabilities to answer this question. The sum of the probabilities has to be equal to 1. Right? So A is equal to 1? No. Does anyone disagree with me on the fact that if I take the summation of both sides, the sum of both sides, what should I get? 1. Does anyone not know this? Don't be shy. I didn't know it when I was of your age. The probabilities have to add up to 1 because that's the law of probabilities. Now if this summation is equal to 1, this is a constant, I can take this out of the summation sign and A would simply be equal to 1 over exponent minus EI kBT. So I take the summation over all the energies of the Boltzmann factor for all the energies, and this particular object in physics, this is called the partition function. Right, so let me suppose I have some atom or some artificial atom for some structure which has only two energy levels, E1 and E2. At what temperature would I have a situation like this? 0 kelvins. At what temperature would I have this situation? Infinite or very large temperature. At what temperature would I have this situation? Not allowed?
Not allowed.
थके हुए हो? Not slept? Not allowed? Any more answers? Not possible? Sorry? How can it happen? Sorry? At lower temperature, lower than what? You can't go lower than 0 kelvins. But she's on the right track, in fact. If you could go to temperatures below 0 kelvins, you would have this situation. Let me show you how. You can look at it from a mathematical perspective. Suppose the fractional population of E2 is N2. The fractional population of E1 is N1. Now N2 is proportional to exponent minus E2 over kBT. N1 is proportional to exponent minus E1 over kBT. Right? N2 over N1 is equal to, it's not now proportional, it's equal to exponent E1 minus E2 over kBT. Alright? You just divide this by this, it's minus E2 minus E1, which is plus E1, right? So this is the ratio of the populations. Generally what we have in equilibrium conditions is that this is less than 1, which means N1 is higher. The lower energy has a higher population. That's the equilibrium situation. That's what the Boltzmann relationship dictates. Correct? That this is less than 1. And this is going to be less than 1 when this number is negative. This number is negative means E2 is greater than E1. So when E2 is greater than E1, which it normally is, then N2 will be less than N1, which means this population will be higher. But what I've drawn here is the opposite situation, which means that this number is greater than 1. The population in the higher level is higher, which means that this factor has to be positive as a whole. But E1 is really less than E2, so the numerator is negative. The denominator has to be negative. So the temperature really has to be negative. So this corresponds to some kind of negative temperatures. minus 1 Kelvin, minus 50 Kelvin, minus 30 Kelvins. I'm going to discuss what this physically means. So if we were to define temperatures as I've defined here, as Boltzmann has defined, that is, the temperature defines the population of energy levels. If we stick to this definition, then yes, this population distribution corresponds to a negative temperature. Alright? So based upon how we've defined temperatures, alright, so this corresponds to a negative temperature, less than 0 kelvins. Now this situation is routinely achieved. It's not uncommon. It's only out of equilibrium. It's a non-equilibrium situation. Boltzmann factors talk about equilibrium situations, but this is out of equilibrium. So this is what normally happens in lasers. You have this condition which is called population inversion. So this is what lasers are based upon. Population inversion. Somehow you go out of equilibrium. You defy Boltzmann relationship. You have more occupancy in the higher level state. You have a negative temperature condition. And this is what lasers are based upon. And we're going to start with lasers in our lecture on Tuesday. We're going to discuss the second law of thermodynamics. And if there are any more questions, I would be happy to answer after the class. So thank you very much.